Hi, my name is Sanket, and today I'll be giving a presentation on our research towards building a practical framework for privacy preserving device logs. This work was performed in collaboration with my colleagues from Stony Brook University and Samsung Research America, and I'm very happy to be giving this presentation as a part of the 2026 PET Symposium. Over the past decade, we have seen our personal devices, like our smartphones, IoT devices, smart home products, increasingly become the target for cybersecurity incidents, to the point where regulatory bodies across the world have now regarded mobile devices to be considered as critical security on endpoints. What that means is these devices are now required to have extensive logging mechanisms and audit requirements, which manufacturers are required to implement on this as a solution. The audit trails are collected from devices either for post-compromise forensics or simply for audit compliance. But the problem here is that these device logs often contain user-sensitive information. Prior research done presented at Usenix Security 2023 shows that Android devices specifically from different manufacturers across different OSs, and irrespective of whether at the application layer or the framework layer, collect a lot of user sensitive information in device logs. And if we are to comply with these audit requirements that are being developed today, these logs will get extracted by the manufacturer and exported to forensic analysis for investigation. So there is this inherent problem of how do we manage our privacy requirements versus our utility requirements, where we know that user sensitive information is present in the logs, but what do we do about it? Well, a simple approach could be to just redact all sensitive data. If you see any user sensitive information being ingested into the logs, you just redact it right then and there. A second approach could be you collect the logs from the device, and on the manufacturer side at the server, you sanitize them using some anonymization scheme or a PII removal scheme. Now, these two approaches can be either a post hoc approach or considered an a priori approach. So let's look at how they actually work. So one of the current state of the art approach here is is a tool called Microsoft Presidio. This tool is currently used by a lot of production software across different companies, which is essentially a post hoc model that is run by data aggregators, where once they have exfiltrated data from the client device, they run it through the Presidio pipeline, which runs a PII analyzer and PII anonymizer to create a redacted form of the data of the logs. But fundamentally, this entire pipeline requires trust on the entire data collection pipeline, which is vulnerable to an honest but curious observer. If I'm the employee of such company, I have access to the full data set. I can easily de-anonymize the data and use it for malicious purposes if I want to. Another approach, which was recently launched by OpenAI with this privacy filter, takes in situ approach for a priori mechanism, where they developed a small language model that can be deployed on customers' end devices, which detects and redacts PII logs on the device before it even gets extracted off the device, with the idea being that data is protected at the source. This approach, however, leads to something known as aggressive sanitization, which breaks a lot of linkage analysis. For example, if I want to figure out where Harry Potter is and if he ended up going into the Chamber of Secrets, how do I know if the Harry Potter tag itself is redacted? Now, so the key insight we developed in this research is that to perform forensic analysis, you need correlation, but not disclosure. Forensic analysis is built on top of a lot of event reconstruction or timeline reconstruction, where if we redact certain elements of the log, it prevents data disclosure, but it also uh, breaks the log fidelity that is needed to correlate certain events. And if the argument is that we can just simply hash the PII values so that you can are still able to correlate, well, then the problem becomes how do we solve anonymity? Because you can, depending on hash values, uh, infer information about the user that that is probably not intended to be disclosed. So the challenge here is how do we balance disclosure of information, or rather a controlled disclosure of information, while enabling correlation. So we developed Proteus as a privacy preserving logging framework uh, to solve this exact problem that allows a forensic analyst to be able to infer data from correlated events without actually disclosing the event itself. Proteus transforms any kind of sensitive data before it even enters the device log. We achieve this by implementing the Proteus layer as a part of the logging daemon that runs on the client devices. Proteus preserves search, debugging, and forensic fidelity of logs, and it prevents plaintext exposure of PIA across any kind of log export, either on device or off device. We implement this across two layers. There is the log processing pipeline, which is implemented on the Proteus client. So you can think of it as the logging daemon, something like logcat on Android. We inject into logcat to collect all the log in situ, detect the PII elements in each and every log export, log statement, then generate a pseudonym variation of that detected PII element using some key K, and then we derive a daily encryption key using a ratcheting protocol that we developed and create a ciphertext of that pseudonym. Now, in the protected logs, the log dump that exists on device, that only contains a ciphertext for the specific PII. The pseudonym is secured locally and the plain text is never exposed in the log dump. So what started off as Harry Potter at the beginning of the logging daemon, what was injected into the logging daemon as Harry Potter, will now be simply a arbitrary ciphertext that does not go back to Harry Potter. On the server side, we developed a log reconstruction pipeline that leverages a protocol we developed called Controlled Disclosure Protocol, where the server can request the client for a specific set of keys that can be used to decrypt the PII values for a given time range. The client provides this set of keys to the server, and the server can only disclose is only able to disclose information for that given time range. Uh, Essentially, the server extracts this protected device logs where they only see the ciphertext related to Harry Potter, and after going through the log reconstruction pipeline, they are only able to recover the pseudonym text that was used, but not the actual PII. We validated our mechanism using a bulk processing pipeline where we leveraged an open source dataset of Android logs to identify what could be whether Proteus adds any substantial bottlenecks. And we found that the overheads due to encryption and further processing is extremely minimal. But in some cases, for example, like the URL, it is actually optimal because the output is truncated to a specific byte size. We also performed on-device measurement using 3 different generations of devices, and we find that across all representative hardware, the identical bottlenecks are in detection and replacement of PII values and key derivation functions, both of which can be implemented as a part of the framework for added latency benefits. Now, the key takeaway behind this entire research is that mobile devices and in general a lot of user devices today are being considered as audit critical systems where manufacturers are incentivized by regulatory frameworks to add pervasive logging into the systems and export the logs out of the device for either audit compliance or post compromise forensics. Proteus is the first framework of its kind that allows protecting sensitive data in logs while preserving full log fidelity required to perform forensic analysis. With that, I thank you for your time to listening into this presentation. If you are interested in this research, please you can find a lot of more information about our mechanism in the paper. And thank you.